Okay, good afternoon. So today we're going to move on to a new topic, the last module of the course, which is NoSQL. So we're going to have 3 classes on NoSQL. First class today, which wraps up the last module of this course. So we're talking about distributed data management, how to have databases over multiple machines. Managing structured or semi-structured data. So in terms of storing structured information, we might think of the classical solution for this is to use a relational database, where everything is ordered in tables, and we have a relational schema, and we have integrity constraints, and we have all this very nice stuff for keeping all of our data nicely ordered. However, with the onset of the web in particular, people started to realize that relational databases were not somehow a one-size-fits-all solution. They weren't suitable for every kind of application out there. So there was this growing realization that in many cases, what we need is maybe something a bit different. And people started to write about this and to state that essentially we need not only relational databases with SQL and this, but we also need some other alternatives. So this was a paper by Michael Stonebreaker and Ugur Demo. So Michael was a Turing Award winner later for his contributions to databases. So one size fits all. The idea was coming to an end. This idea that all we need for data management is a relational database and we're done. So SQL has some advantages and disadvantages. In terms of advantages, it's a declarative language and it's highly expressive. So using SQL, we can write complex queries, we can state what we want, and then we can delegate to the database system the process of optimizing and figuring out the best way to get what we want. However, SQL is, because it's a very expressive language, it's difficult to optimize. It's not easy, especially for more complex queries, to find the best plan. And it's, more importantly for us, difficult to distribute. So essentially, if we want to make use of multiple machines, because of the complexity of the SQL language, it's not that easy to get SQL running in an efficient way over multiple machines. For example, to do joins across multiple machines. So we also have in relational databases, we have the notion of ACID, of transactions, which is great because this guarantees correct behavior. And it allows us to support transactions where we can, for example, run multiple smaller operations as if they were a single operation atomically. The cost of this is that, okay, they're very costly to implement. It has quite a lot of overhead to provide these guarantees, and also providing ACID guarantees over multiple machines in a distributed setting is quite difficult. So we have different types of guarantees we could look at. So based on this paper, just to give an idea of some of the transactional overhead. So in this paper, they did some analysis, taking an in-memory database, which I think is important to mention. But the work of essentially giving the ACID guarantees and of supporting transactions was deemed to be quite high. So actually we see that they measured the time and they figured that about 6.8% of the actual work that was being done in this in-memory database related to actually getting the results for queries, for example, or inserting data. The rest essentially were costs relating to transactions. So with transactions and ACID, one could process 640 transactions per second. Without ACID, turning off transactions. So happy birthday, what did they sing? Without transactions, the database could process up to 12,000 transactions per second. Okay, so transactions have a high overhead. ACID has a high overhead. SQL, very convenient, but has a high overhead as well. So what are some alternatives to relational databases for big data? You might have heard of NoSQL. Has anyone heard of NoSQL? No? So good. Okay, so what is NoSQL? NoSQL does not mean no SQL. NoSQL means not only SQL. Yeah, in theory at least. So the idea is not to say that SQL is a bad thing or nothing like that. SQL is still widely used and very successful. The idea is to say that we need other things besides SQL sometimes. Yeah, so not only SQL is the philosophy behind this movement. So if we look at a list of some of the most popular databases out there, we see that here we have a list of the top 20 from this website, which takes some rankings based on how many searches there are about that engine, how many questions on Stack Overflow, and so forth, to somehow get an idea or an indicator, an estimate of the popularity of the system. So we see here the top 20 systems. We see Oracle in first place, followed by MySQL, which is a close second, followed by Microsoft SQL Server, followed by Postgres, followed by MongoDB. And MongoDB is the first system here that we see is a little bit different to the other ones, in that the first four are relational systems, relational databases, SQL type systems. And MongoDB is the first database we see that is not a relational SQL style system. Yeah, it is a NoSQL system. So in fifth place, we already see a NoSQL system. Relational databases are still super popular, but now we have these NoSQL systems that are becoming increasingly popular as well. If we continue, we see that number 6 is a key value store. This is another type of NoSQL system. Then we have a DB2, which is a relational system. Then we have Elasticsearch, which we already used in the last 2 labs, which is essentially a search engine, or what they would call a document store, where we can index documents. Then again, we have 2 more relational databases. And then moving down, we see another NoSQL system here, which is Cassandra. And moving down again, we see Splunk, which is another search engine like Elasticsearch, and so forth, right? So in the labs, we're going to be playing in the next lab with Cassandra. Thereafter, we're going to look at MongoDB in the next class and lab. And then afterwards, we're going to look for Neo4j, which used to be in the top 20. I guess it's like position 21 or 22, which is a graph database. Yeah. So in terms of NoSQL, we see that different systems have different trade-offs. Yeah. So we have a different list of features, and we have different levels of scale and performance. Yeah. So essentially what we see in terms of NoSQL systems is that they are often, but not always, distributed. They are often built on top of simpler languages than SQL. How simple depends on the trade-off for the system. And there are different flavors that can be useful for different scenarios. So depending on what we would like to do, we might choose a different NoSQL system. So in terms of the trade-offs, I mentioned this trade-off that essentially these NoSQL systems tend to trade off 2 dimensions. So one dimension is size or scale, yeah, and the other is complexity, yeah. So here we have 4 very high-level categories of NoSQL systems. So we have key value stores, column families, document databases, and graph databases. So graph databases are the most complex of these categories of NoSQL systems. So we see that they're more complex, which means that we'll be able to solve more complex queries using them. However, this comes at the cost of decreased scale. So if we really want high scalability and efficiency, key value stores are the way to go, but they are exceedingly simple, yeah, as we'll see soon. So we have these 4 main flavors, and we see that they provide different trade-offs in terms of scale and complexity. Before we continue to talk about NoSQL systems in practice and key value stores, it's important to introduce an influential topic in the case of distributed NoSQL stores and distributed systems in general, which is the notion of the CAP theorem. Yeah. So in relational databases, we can talk about ACID. In distributed systems, it makes more sense to talk about CAP, especially for distributed databases. So CAP basically refers to 3 guarantees that a distributed system could make. The first is consistency. And consistency in this case is a little bit different to the consistency in ACID. Here we say that all nodes in the distributed, all machines in the distributed system should have a consistent view of the system, of the state of the system. Yeah, so if we ask different nodes the same question, we should expect the same answer. Availability. So this is the idea that we want to have available systems that respond a very high percentage of the time. Yeah. So availability is the binary or Boolean version of that, which is basically saying it's a guarantee that every read or write is acted upon, that we don't reject any requests. And partition tolerance. Since we're in a distributed system, P means partition tolerance, which means that the system will continue to work and to provide these guarantees even if messages are lost. So a partition is considered to be a partition of the network, where we have machines on different sides that cannot communicate with each other. So C and A here are not the same as A and C and ACID. So they are different concepts. So atomicity and ACID, consistency, isolation, and durability. So the A actually is even a different word. C is consistency in both, but they have related but different meanings in CAP and ACID. Okay. So let's assume we have a distributed system and we have some replication. We have a replication factor of 2, which is maybe not the wisest replication factor, as we'll talk about a little bit later. But we have 2 copies of our data, so we're robust to failure. Yeah, so we can handle some sorts of failures. What kinds of failures? We'll discuss that soon. So we have partitioning as well. So we have here all the data for users that start from A to E. Here are the users from F to J, here users K to S, and here users T to Z. So hopefully this is well balanced. In a real system, we might prefer to use a hash modulo function to do the partitioning, but for the example, we'll assume that they're partitioned in this way. So what does consistency mean here? Consistency means that basically all of the nodes, all of the machines in this distributed system have a common view of what is the state of the system. Yeah, for example, there are 891 users whose username starts with M, right? So they have a consistent view of the state of the system, the database, for example. Availability means that as a distributed system, not the individual nodes, but the distributed system itself should respond to all requests. Yeah, so it should stay up and running and available. So if a user asks, a client comes and asks maybe via the web, a web application, or maybe via some other interface, how many users start with M, or makes any request maybe for insertion or deletion, then we would expect that the answer should be given as such, 891. Okay. So the requests of the clients are responded to. The last thing is partition tolerance, which basically means that if for some reason some machines cannot communicate within this distributed system, and there can be many causes for this, such as a hardware failure, a software failure, or the more common case where there's just a whole lot of traffic and there's no way to be able to respond to everything sufficiently quickly. So the distributed system is flooded with messages effectively. In the case of a partition like this, what we want to have is that the system continues to work and continues to be consistent and to be available. Yeah. So the CAP question in terms of the theorem is, can a distributed system guarantee consistency, availability, and partition tolerance at the same time? So what do you think? You think it's possible? Yeah, maybe. It's not possible. Yeah, so it's not possible. So as we would say in English, nope, or I don't know, maybe is it in Peru? They say nope. Nope. No. Okay, so the CAP theorem. So a distributed system cannot guarantee consistency, availability, and partition tolerance at the same time. And it's more or less maybe intuitive. We'll have a look at a sort of a sketch of a proof in a second. But the important thing is that when this was published, there were systems being released that were promising these 3 things. And that didn't seem to be possible. So people felt it important to formalize this theorem. Deutsch. So the CAP proof, just to briefly go through what an argument as to why this is not the case. I put it in inverted commas. It's not very formal, but it gives the idea. So we start off with our distributed system and it already has some state and we have consistency and everything is fine and everything is working wonderfully. Now we introduce a partition, which has to satisfy the P. We can have partitions. So we have a partition in our system. Now we add Madonna, and Madonna gets added to one side of the distributed system, right? So essentially we have some sort of request, or we have some request to add a new user, and based on availability, we have to respond to this request, right? We can't reject it. So we can't say, oh no, we have a partition at the moment, we're going to reject your request. No, we have to process the request, which means that somehow now we have this impossible situation where we can't update the state on both sides of the partition. Yeah. So what this means now is that if we get another petition, for example, asking how many users start with M, then we could get, if we ask the wrong side of the partition, we could get old information, 891 rather than 892. Yeah. So this is the main idea, hopefully relatively intuitive, that if we have partitions, there's no way we can offer consistency and availability at the same time, right? The most important practical outcome of this is that we need to choose two. So it means that we choose AC, CP, or AP. Yeah. So we can have three options, more or less. It's a little bit more complicated than that, which we'll see. But there's no intersection here. So a CA system, a system that offers both consistency and availability, guarantees to give a correct solution, but only while the network works fine. Yeah, so this is sort of your typical, let's say, relational database on one machine or what have you, where you don't have partitions. CP guarantees that responses are correct, even if there are network failures, but responses may fail. So in the previous scenario we saw, what will happen is if we try to add Madonna, we'll say, no, sorry, our system's not available at the moment. There's a partition. We're not going to be able to maintain consistency. So we reject some requests that we fear might break consistency. We can also have AP, which provides a best effort response even in the presence of network failure. So that's similar to the scenario we saw in the last part, where we did not give a consistent response, but we gave a good enough response. Yeah, we're missing some of the most recent inserts, but we gave somehow a best effort response. So AP is very common, in particular for web applications, for example, for Amazon, for Twitter, for whatever. They want to keep high availability. They want to try to continue to always service requests. And sometimes they will do that at the cost of consistency. Yeah. For other applications, we may want to put a stronger emphasis on consistency. For example, if we're dealing with important client data or account information or some sorts of details of that kind, we may prefer a CP system. So a CA system, essentially, in this case, what it means is that there's no partitions and everybody lived happily ever after. There's no problem. A CP system, in this case, means that we're going to reject either the request to add Madonna or the request to read the data from the partition system. Yeah, we're going to say we can't respond to this right now. So essentially, the CP system can say error, or I can't do that for you right now. The AP system will give the best effort response, even though it's not necessarily consistent. So we'll say 891. There is another important notion in these sorts of distributed NoSQL systems, distributed databases in particular, the notion of base. So this is, I think, some clever play on words, because we have acid in relational databases and base is the opposite, alkalino of acid, right? So we have base in the case of these systems. Base stands for basically available soft state eventual consistency. So basically available means it's almost always up. Yeah, maybe it's down sometimes, but we get what, have you heard of the nines notation? 3 nines, 4 nines, 5 nines. So 5 nines, for example, I often use it for discussing availability, where 5 nines means 99.999% of the time it's available. It's how many nines you get in the percentage. Yeah. So 5 nines, 6 nines, 7 nines, people usually talk about that. So that's what basically available means. Let's say 5 nines or 6 nines or whatever. We have soft state, which means that we have replicated cached data. So we have some data that may not be the most up to date. It means that we have copies of data in different places. We maybe have some computed data. So we have some cached data that maybe is not the most recent. And then we have eventual consistency, which means that we will allow stale data for now, but eventually the data will be updated and everything will become consistent. So the system is always converging towards consistency. And if we could pause all of the external requests coming for a moment, it would reach a consistent state eventually. Yeah. This is similar to the scenario we saw, where maybe if we have a partition, we try to accept the request to add Madonna and we return an old count. Yeah, so the consistency is not strong, it's eventually, if we wait long enough, the partition will hopefully disappear and we'll get everything will update again and we'll get the correct answer. So in what way does Twitter act as a base or AP system is the question. So a lot of web applications function in this base, under this base paradigm. Yeah. So we'll look at Twitter and we'll see. So if we look at Twitter and look at a real world example, of course, machines fail, networks fail, and so forth. However, even just someone creating a tweet, so somebody writing a tweet with a high number of followers can create a partition because it will create so many messages. If you remember in Twitter, when somebody writes a tweet, we're going to write it many times to the different accounts that follow that user. Yeah. So if Barack Obama tweets, then we're going to write in all of the timelines of the users who follow Barack Obama, the 129 million users, into their timelines, we're going to write that tweet. As a result of this, I don't know if people here use Twitter a lot or not, but sometimes users may see retweets of celebrity tweets before the original tweet. Yeah, so you might actually see a retweet of someone that you also follow, and then later you get the original tweet. So this is a classic example of base. This is a classic example of, rather than rejecting your request for a timeline because somebody has posted, basically this is giving you the best effort available data right now. And if you leave it long enough, the IDs in Twitter are sequential, so they can be reordered to give a more consistent view. So this is a classic sort of base scenario. And obviously it's much better that you receive some timeline, even if it's maybe not the most consistent, that you receive some tweets to read rather than just saying, sorry, there's a partition at the moment, or we're processing some tweets, so we can't give you a perfectly consistent timeline. Okay. So in practical distributed systems, I presented it somewhat as a Boolean choice or choose two. In reality, in practical distributed systems, we have to fix P because partitions are a reality in distributed systems. There's no way to avoid partitions. Yeah. So P is, there's no real choice if we're going to have partitions. And then the idea is that we want to choose some sort of trade-off point between C and A. Yeah, it's not that we have to choose A or C. We can maybe choose some point between these two continuums, between these two goals. So we could maybe choose something in the middle that is sort of available, sort of consistent, or we could choose something that's more strongly consistent, or we could choose something that's more strongly available. So we have this classic trade-off between consistency, always giving the correct answer, precise answer, versus availability, responding to all requests, even if we respond in a way that's not entirely consistent or up to date. Any questions or doubts so far? All good. Okay, so then we have, what does it mean, partition tolerance? So we're going to talk a little bit briefly about different types of errors or faults. So if we think about faults, maybe your hard disk has melted, or computer or machine has melted, or maybe some rats have gotten into, chew some cables. Maybe somebody installed Windows on one of the machines by accident. Maybe it got flooded. Maybe there was, I don't know, whatever happened here. So we can think of lots of different faults in practice, yeah, physical faults. But what we're actually more interested in conceptually are two different types of faults. The first type of fault is called a fail stop fault. So this is where a machine just completely fails to respond or times out, like many of the instances we saw before, the actual causes. So this is often due to the hardware or to load. Yeah, so the machine is just overclocked and the machine is just too busy and can't respond at the moment. So let's say if we're doing a word count or we're doing some sort of task and we have two machines, we want to retrieve some data or to do some processing on the machines and get some results. If one machine fails, then the other machine, we can rely on the second machine, in this case with a replication of 2, in order to return the correct result. So in this case, once we get the result from one of the machines, we're good. Yeah, we're fine. So this means that we need at least F plus 1 replicated machines in order to continue to work in the case of fail stop faults, where F is the number of fail stop faults. So in this case, F equals to 1. We've had one fail stop fault. We just need one more machine than the number of faults and we're good. We just need one machine to work. Yep. So this is the fail stop fault scenario. There is a second type of fault called Byzantine faults. So the name is kind of relating to Byzantine general problem in distributed systems. But the idea is effectively the idea that a machine can respond incorrectly or maliciously. Yeah. So in this case, it's a little bit more complex. What happens is we don't necessarily know which machine has failed, if it has failed or not. Rather, we have this two different results or two different responses are given by the two different machines. Yeah. So what does this mean? What does it mean for the client? Why is it more complex? We don't know which results are correct. Yeah. So it's more difficult to handle these Byzantine faults than the fail stop faults. So how many, if we have F Byzantine faults, how many machines would we need to know what the correct answer is? Three. In this case, we would need three. Yeah. So, and if we take F equals 1 here, it would be? Yeah, 2F plus 1. Yeah. So in this case, we have F equals 1 and we need 3. So in the general case, what we're going to need is 2F plus 1. So if we have 3 machines here, we know that there is at most 1 fault, then we're fine. 1 Byzantine fault. So how many working machines do we need in the general case to be robust against this? We need at least 2F plus 1 replicated machines. So if we wanted to be tolerant to up to 2 Byzantine faults, we would need a replication factor of 5, 3, 7, and so forth, because we need the Byzantine faults. In the worst case, they coincide and they give the same value. We need more machines to give the correct answer. And then we can take the majority and we can be robust to these sorts of failures. So many people, maybe you've also asked during this part of the course, why do we set replication factors as 3? Why not 2? And the main reason is for this sort of problem. Yeah, so 3 is the minimum. With a replication factor of 3, we can be robust to 1 fault. It can be either a fail stop fault, of course, or a Byzantine fault. So we're robust to at least one fault with 3 machines. Why does that happen? I'm not sure. Maybe you're talking about, I'm not sure what you, in the chat, what you thought that was in reference to, but maybe Windows, somebody installed Windows. I'm not sure why that happens. I'm running Windows on my machine here as well. So, okay. So this gives rise to a notion of distributed consensus. So we have different types of faults. We can have different numbers of faults. We can have different sorts of scenarios. So how do we choose this trade-off? How do we find this trade-off between consistency and availability? So here we have the classic dress. I'm sure you've all seen it before. If not, it might be a bit surprising. So people typically say pick one of 2 options here. So we'll do a little survey. We can also do it in Zoom on the chat. You can type in your answer. You can raise your hand. Who here thinks it's blue and black? 1, 2, 3, 4, 5. Who here? 6. Who here thinks it's white and gold? 1, 2, 3, 4. I know these people are strange. So, okay, so we have 6 against 4, 6 for blue and black. What about in the chat? No answers in the chat at the moment. Okay. Okay. So, what happens? We're a distributed system. We disagree on the colors. We have 6 against 4. So we have 6 against 5 now, including the chat. So do we have consensus? Can we decide on the color? As a distributed system, do we agree? Do we proceed? Do we not proceed? And this depends largely on the notion of distributed consensus. So it depends on what technical definition we give, and the technical definition we give for the consensus will lead to different levels of consistency versus availability in a system. Yeah. So this core idea of distributed consensus is the basis of the AC trade-off, the availability consistency trade-off. The strongest and most consistent level of consensus we can have is a strong consensus where all nodes need to agree. Yeah. So in this case, do we have, in the case of the dress, do we have strong consensus? Absolutely not. Yeah. So in this case, strong consensus means we, for example, all say blue, and then we have consensus. Otherwise, if we change one of them, then we have no consensus, right? So we have 1 white and 4 blues here. Okay. The next type of consensus we have is a majority consensus, which states that a majority of nodes need to agree. Yeah. So in the case of the dress, there are sometimes people who see it as a third option. I think it's blue and white or blue and gold or something, but okay. In this case, since we had only 2 options, we have an odd number of people, 6 and 5, 11 responded, then we have a majority consensus in this case. So in other times, like in this course, there wasn't a majority, but okay, in this case, yes. So we have consensus. We have 3 out of 5 in this case on the slide. Agree on the blue value. The value is not important for whether there is a consensus or not. If we change one of the whites to one of the blues to a white, then here again we still have a majority consensus, right? Because the value is different. We've decided on a different value, but there is a majority consensus this time for white. In this case, is there a majority consensus? No. No consensus, we haven't reached a majority. Okay. So next we have a plurality consensus. I don't know if you've heard of the word plurality before. Mayoría simple, I think it might be called a pluralidad, maybe in Spanish. So plurality is this idea that there is one unique option with more votes or more responses than the others, but it hasn't necessarily reached an overall majority. Yeah. So in this case, we have blue with 2 responses, and then we have orange, white, and green. And what we need is a plurality of nodes need to agree. So we see that in terms of the maximum votes or the maximum responses is for blue, and it's unique in that sense. There's no tie at the top. So there is a consensus. There is a clear plurality here. In this case, is there a plurality? No, because blue and white are tied at the top for 2. Yeah, so there's no clear winner here. So there's no consensus in this case. A very common type of consensus in distributed systems. Okay, majority and a strong consensus are very popular. However, quorum consensus is also very popular, where we set an N. We say how many nodes we need to agree for something to be accepted. So if we define here N equals, for example, 3, there's consensus. If we define N equals 4, we don't reach consensus. We don't find 4 nodes, at least 4 nodes that agree on a particular value. So N equals 2, we also have consensus in this case, because what will happen in the quorum is that we're going to ask or receive the responses from the machines in order. The most typical thing that we will do with quorum with N equals 2 is we're just going to ask 2 machines. We're not even going to bother continuing, okay? So we'll ask 2 machines and then we can get a consensus. So if we ask the first 2 machines, just to clarify, sorry, and we get 1 vote for one and 1 vote for the other, we can continue and ask a third machine, and maybe we get another vote. So maybe we ask this machine here and we get white, and this machine here and we get blue, this machine here and we get green. We can continue and ask another machine, and okay, now this one says blue, so we have 2 blues. Blue reaches the quorum and we accept blue as the answer going forward. Yeah, it could also happen the other way. We could ask white, blue, green, and then ask white, and then we will accept white to be the answer. Yeah. So there is consensus here, but it's not unique. We could end up getting white as our answer or blue as our answer with N equals 2. So what value of N would we need for a unique consensus with N nodes, capital N nodes? So N equals 5 here. We have 5 nodes. What value of N would we need to define for the quorum to be sure that it's unique? 3, yeah. So it would be same as majority. We need more than half, yeah? Yeah. So N has to be greater than N over 2, yeah? So we need 3 in this case, or we need more than half in the general case. Okay. So the weakest form of consensus is just turn consensus off, essentially, or just take the first answer. So in the case of the dress, I would just ask one of you, what color is the dress? You would tell me, and that's the answer I accept. Yeah. So not very strong consensus, but okay, it's at least I get a value. Yeah. So in this case, is there consensus? Yep, there's consensus. There's always consensus. What value will we take? It just depends on what machine we ask or what machine responds first. So we see different notions of distributed consensus, and basically this gives us the trade-off for CP versus AP. So for consistency with partition tolerance, versus availability with partition tolerance, where we see that the most consistent is the strong consensus, where we will need all nodes to agree on a particular value before accepting it, to consensus off, where we just take whatever answer we get and we return that, and hopefully it's correct. Okay, and in the case of let's say we have strong consensus is our policy, and we ask a question and we get different answers, then our response in the case of consistency with partition tolerance of CP would be to say, no response, we don't know. We don't have to answer the request, right? Okay, in terms of scale, which do you think is more efficient? The ones at the bottom, yeah? So we have a lot fewer messages to go around. We have to send a lot fewer messages in the network. We have, each machine has to do a lot less work. So the cheapest by far is just turn consensus off. We trust whatever the first answer we can get is. We don't ask any more questions. Okay, so the choice is application dependent. Many NoSQL stores allow you to choose the level of consensus and replication. They might not tell you, do you want AP or CP, but they'll say, what value of N do you want for your quorum? Do you want majority quorum? Do you want strong consensus? This sort of stuff. So you can often configure this, and also not just at the level of the store, but the level of the particular table or collection of data. You can set different options. Any questions or thoughts about that? Okay, so that's the core kind of theory or background of NoSQL systems that we need to kind of cover as context. This would be very important in terms of if you're administering a NoSQL store or you're trying to choose between different NoSQL solutions. These sorts of topics are very common to encounter. So the next topic we're looking at then are the specific types of stores that we can have. We're going to talk about two today. We're going to talk about the third in the next class, and we're going to talk about the fourth in the class after that. Yeah. So the first category, there are four categories. First category we're going to look at are key value stores. Yeah. These are the simplest and the most scalable in general as a principle. So what is a key value store? It's basically a fancy name for a map or an associated array or a dictionary where we have keys and values. Yeah, very simple. So we put some key with some value into the map. We can get for a given key its value, and we can delete the data associated with the given key. So one thing to mention is that sometimes these key value stores will also support versioning. So when you do put, and let's say the key already exists, then rather than delete the old key or overwrite the value for the key, you version it and say, oh, okay, we'll store this as an older version. Essentially, the main model, I wanted to say the key model, the main model is just keys and values. Yeah. We can do a lot with the map, however. Yeah, so we can have pretty complex values that are not just a single value for maybe population or something, but we could have a JSON document, or we could have some XML document, or we could have some structure there where we encode quite a lot of information in the value. So here we have some countries and cities, some users. So we were indicating different types based on some prefixes, and then the value. And here we have some sort of syntax which allows us to extract information about the capitals of countries, what continent they're on, their population in a given year, and so forth. So the value can be not a simple value, but rather a complex value. So in some sense, we can model pretty much anything we want in a map. We could, just get rid of completely relational databases and all that relational model stuff, and we could build all of our data in a map. The problem is that sometimes it would end up being pretty redundant, maybe inefficient, and we need to do a lot of low-level hacking to be able to interpret the values and to extract, for example, the population. We need to read this value, and then we need some code to parse this out, and then to recognize where the population values are. So this is a very simple model. What was its origin? To maybe motivate a little bit of real-world scenario where this came about. So Amazon, as you may have, I'm sure you're aware of Amazon, very large online retailer. Started off selling books and then started selling all sorts of stuff. They manage lots of information about products and also shopping carts and customer information and all this sort of data. They also need to support, for example, certain types of analytics, for example, to be able to recommend if you're shopping for a product to try to get you to buy more things by recommending you things that other people who bought that product also bought. So Amazon experienced pretty rapid growth, especially around this period here. So I should mention that this is some years, there's gaps here in the years in case you see jumps. So here there's a jump. However, it experienced pretty rapid growth. Here's up to 2014, but it's continued to grow even more due to certain business practices. But anyways, so essentially around this time here, the Amazon tech people, the computer scientists, the people who are working in Amazon in terms of the online store and the services provided and so forth, they were really starting to struggle to cope with the scale. So in general as well, aside from the Amazon online store, we also have Amazon Web Services, which was becoming popular at that stage, where you can rent machines, you can have your own cloud instances hosted by Amazon and pay for that. So in this scenario, there was a lot of demand and they were using relational databases, mainly with some sort of scripts to partition the databases on different machines. So the databases were struggling. And Amazon realized that really this overhead of using relational databases is just too much. So they realized that they didn't really need SQL. What they needed most times is just a map, because let's say you have a product ID, you're in your web application, you receive an ID for a product. What do you want? You want to get the name of the product, the price, the image, the blah, blah, blah. So you have an ID and you just want to get back the information about that. You have a customer ID. A customer logs in. What do you need? Given the customer ID, you just want all the data for the customer. Yeah. You don't need to do joins and then aggregations and order by and group by and all this sort of stuff at runtime. Yeah. So Amazon realized that really all they need in terms of a database is a map. They just need, given some ID, get me some data back. They also realized that for certain scenarios, they didn't even really need transactions, strong consistency and so forth. So for example, for things like recommendations, it doesn't really matter if the recommendations are super consistent. It's just if they're good enough, they're okay, right? So some savings could be made in terms of asset and transactions and consistency. So their solution to address the scale problem around 2007, before that they had been developing the solution, but they published a white paper in 2007 entitled Dynamo, Amazon's highly available key value store. So this was a pretty influential paper that led to various implementations, open source implementations, and later Amazon also released a DynamoDB, a sort of a later version of this database. So the goals of this were scalability, so to be able to grow, and if they needed more scale, that they could add more machines and that the system should scale with that. High availability, so if you use Amazon, you want to know that it will be up, and it's quite always a remarkable situation nowadays when one of these major websites is not available. So we have a high number of nines in terms of availability and performance. Yeah, we want the data to be returned very quickly. So what do we pay for that? These things don't come for free. What we're going to pay is SQL. We're not going to have our declarative nice language anymore. We're going to do things at a more lower level, and we don't need full asset. Yeah, so we can somehow trade away some transactional details. So in terms of distribution, how might we distribute a key value store over multiple machines? So let's say we have 4 machines here and we have our key value store. How do we do it? We can just take the hash on the key. Yeah, so it's pretty natural based on what we saw with MapReduce. So we can take the hash on the key and we can distribute it over the machines. There is a second option that we'll see a little bit later. That's not as intuitive, but it can work out pretty well sometimes. But here we were going to hash on the key and take the mod m. In this case, m is 4, the number of machines. So, okay, now we have a problem. Let's say we do this, and it's a little bit different, this scenario, to MapReduce or Spark. Why? Because now the data are persistent. We want to store the data over a long time. So what happens if a machine leaves or joins? If we really want to scale, then we want to be able to add more machines and do it in a transparent way. So let's say we added a 5th machine here, for example. What would happen? If we added a 5th machine, then the value for m becomes 5 and sorry? Not as such. So the problem would be now that all of the machines we chose before, they're now obsolete. Because if we take mod 4 and we change it to mod 5, then all of the keys, the hashes, the answer for this function for all of the machines, it changes. Yeah. So maybe if we're careful, it could overwrite data, but we have to handle this case to say, what are we going to do? So we would need to rehash everything in theory. Yeah. This is not such a problem for Spark or for MapReduce because we're running a process. We take all the data, it's closed, we hash everything, and then we finish. But here we could be adding more data in the future. We could be adding more machines. So we need a scheme whereby we don't run into this problem and we don't have to rehash everything. Yeah. So how can we avoid rehashing everything is the question. So the answer to this is to apply what is called consistent hashing. And the goal is to avoid rehashing everything. So the solution is relatively straightforward, even though if you were to sit and think about it for a while, it doesn't seem obvious. The solution is pretty elegant. So we're going to hash using a ring. So when I say a ring, it can just be like a clock. So that goes from 0 or 1 to 12. We have some sort of range of values, maybe from 0 to 1, or from 0 to 65,536, or 0 to whatever we want. And we assume it loops back to 0. Yeah, so it sort of creates this ring. So we hash using a ring. So here we have our ring. So let's say this is 0, and this is also 1. So when we get to 1, it just loops back and continues. So we hash using a ring. So what are these dots here? Each machine picks n pseudo-random points on the ring. So in this case, we have 3 machines that are the different colors indicated here. And each machine in this case will select 4 points. So it will pseudo-randomly choose 4 values in this range that will form 4 points on the ring. So essentially, these points then indicate the responsibility of the machine. So we say that in this section here, the red machine will take care of this. This blue section here, this blue arc of the ring, the blue machine takes care of this. And in this this segment here, the green machine will take care of it. So objects are then mapped to the ring. So for example, the keys of our key value pairs, we can take our keys and we can hash them and we can map them to some value on the ring. Yeah, so these are the gray elements here. So we have 1, 2, 3, 4, 5, 6 keys. And effectively, this decides on what machine we're going to send the data. So we have this one, the green machine, this one, the green machine, these 2 on the green machine. Okay, we have a lot on the green machine, this one on the blue machine, and this one on the red machine. The idea now is that if a machine leaves, its range can be moved to the previous machine. So if, for example, we were to get rid of, let's say, the red machine here, then this point would move to the blue machine that came before it. Yeah. So we don't need to rehash everything. We just need to move the objects that were assigned to the particular machine. And we can do that automatically by just assigning its range to the previous machine in the ring. If a machine joins, it picks new points and it takes the responsibility for the objects that are then assigned to it because of that. Yeah. So we don't need to rehash everything. This is consistent hashing. We use a hash ring essentially to avoid having to hash everything again. Okay. Any questions or doubts about that? Okay, so in Amazon Dynamo, we also have a replication factor, which is super important to avoid data loss, to ensure high availability and so forth. In general, you can set the replication factor as you like for a given map. In this, as is typical, a typical factor would be 3, so we're tolerant to at least 1 fault, including a Byzantine fault. So commonly there would be primary and secondary replicas. So it means basically that we have one copy of the data that's in control of the changes to that part. It controls the that copy or that part of the map, and the primary replica can be elected from secondary replicas in the case of failure of the primary. Okay. So we have some replication factor. So how does the replication work in the case of the consistent hashing? The idea is that if we have a replication factor of 3, then we could continue on the ring. So let's say we have an object here, which is the green thing. If we wanted to have a replication factor of 2, we have to choose a direction. So let's just say clockwise. We go clockwise n times until we get n machines. Yeah, so if we had n equals 2, we would start here. We have 1 machine here, which is green. And if we need 2 machines, we just continue clockwise. And then we put it in we assign it also to the right machine. Yeah. So we'll continue clockwise or anti-clockwise, whichever we choose, around the ring from the point until we get n unique machines. And then that's what we're going to replicate. Here, n equals 3 would be a bit boring because we only have 3 machines, but okay. So the model in terms of what Amazon Dynamo allows us to store, we essentially have tables, which are just with 2 columns. We have a primary key and we have a value. Yeah, so it's essentially a map masquerading as a table. So the primary key is hashed or unordered. Yeah, so we don't have any order implicit in the map. Yeah, so we can have maybe one table or map for countries, another table or map for cities, and so forth. So in terms of the CAP system, we can have 2 options for each table. We can have a CP system. So what's a CP system again? So it's consistency. Oh, answer the other one first. What's an AP system again? An AP system is means that we have eventual consistency and high availability. So we're always trying to give answers, even if they're not the most accurate, always. And then the CP system, we have the option for that, which would be the strong consistency with lower availability. So we're a bit more careful about what we return, possibly even rejecting requests if we're not sure. In terms of consistency, there's a few other elements that Amazon Dynamo uses in order to guarantee consistency. One of these is called a vector clock, which basically keeps track of which nodes or which servers, in this case it uses S, are modifying which data. So let's say we have some data, some value, for example, the content of a shopping cart. Yeah, so we have D1, and D1 is the ID of the shopping cart, and we want to, or D, sorry, is the ID of the shopping cart. Then let's say we have server X, it writes something to D, or it changes D, the shopping cart. So then we say we increment the number of times or modifications for server X of the D shopping cart, and that creates a second version D2 of the shopping cart D. So what we're doing is every time that this shopping cart D is modified by a server, we add to the vector clock a +1 for that server's ID. So we say, in this case, let's say that there's 2 branching changes which could cause problems. We have a branching change where S is modified by server Z, and here S shopping cart D is modified by server Y. So we add SY1 here and we add SZ1 here, which gives us some information that in this version, D has been modified by X twice and by Z once, and here it's been modified by X twice and Y once. So then we can actually, using these vector clocks, see that these are incompatible versions, that somehow some branches happened and these are not compatible. We can also see if it's an older version, maybe it's an ancestor version that came from somewhere. So we can use these vector clocks to track modifications on different servers in a distributed setting, and then detect that, okay, these are actually branching versions that may be incompatible. And we could try to reconcile them by merging them somehow. So in terms of reconciliation and consistency, what would happen in this case? It could happen that we have 2 versions of one shopping cart because there was modifications in different parts of the distributed system. So here we have 2 shopping carts, and the question is, how should we merge these? How should we merge multiple conflicting versions of a value? For example, if D is our shopping cart here, and now we have 2 different shopping carts, what should we do? So there's, yeah. So this is called reconciliation, where we see two branches have occurred of something and we need to reconcile them. So one option would be, let's say we want to take the union. Yeah, so now maybe the shopping cart should contain all the products. Or should we take the intersection? Should we just take the things that are in both? Yeah, so the most common generic way to do reconciliation, if we want to do automatic reconciliation, is to take the most recent one. So it's the last timestamp wins. So whatever was the last timestamp, we take that because it's probably the last thing the user would see. However, oftentimes as well, reconciliation, we can't rely on a policy. We need some application logic. So it means that an application will need to decide what to do. So Dynamo offers this last timestamp wins reconciliation, where we just say whatever was the last thing that was updated, that wins. But it also supports application specific logic for consistency. In terms of consistency as well, if we have replication, what we would like to know is that they're actually replicas. They're actually replicating each other, that they're copies of each other. So let's say we had two large files or two large indexes here of these maps. So we have two copies on two different machines. How can we efficiently verify that two copies of a block of data are the same and find where the differences are? So essentially, we'd like to know, are these two copies of this file or this index, are these the same? And if they're not the same, where are they different, right? So there's some structures that we can use for that. The most commonly used, which is also used in the case of distributed ledgers, Bitcoin, and so forth, is the notion of Merkle trees. So a Merkle tree is effectively a hash tree where we have our underlying data here. We have values A, B, C, D, E, F, G, and so forth. And then we take hashes. So we take hashes of individual data points or individual lines or individual blocks or whatever unit of data we want as our base. We take the hashes of those individual things, and then we hash the combinations. We can hash 2, 3, some B value. So in this case, we're hashing pairs. So now we have a hash, which is a hash of A and the hash of B. So we have hash AB. And then as we go up the tree, we have hash ABCD, hash ABCDEFGH, and then finally the root, which is somehow encoding the entire file. Okay. So if we have two Merkle trees for two different files, what we can do is start at the root and check the roots to see if they're different. If they're different, it means the files must be different somewhere. We can then descend the tree to find out where they're different. So let's say they're different at the root. If we go to the left, we see that this hash is the same. So we can rule out the first half of the file and say, okay, the difference must be here. So we see that this is different. And then if we go down, we can identify precisely where the differences are, in an efficient way. So that's a flavor of some of the stuff that we have in Dynamo. So in general, I won't talk too much about implementation. Maybe I'll mention a couple of features, but yeah, so if you want to learn more about how Dynamo is designed and implemented, how it's used, you can also check out the white paper. This was influential and inspired quite a number of open source implementations that took the design choices of Dynamo. Some of these were, for example, React, which is a popular key value store used by these companies. Open source, now it's open source. Redis, another open source key value store, mainly focused on in-memory storage rather than on disk, so it's not persistent. It's mainly used for caching, for example. If you wanted to, if you created some object, maybe an object for, I don't know, stock exchange, a question object, yeah, and you wanted to cache that, you could use maybe something like Redis, and it would be cached in memory for you. And then you could just invalidate it when the question was updated, for example. Cassandra is a key value store used by all these different companies, lots of logos. It eventually evolved more into a tabular store, which is the second category we're going to look into. Cassandra is also the system we're going to look at in the lab. So the second category that we're going to cover is the tabular. It has various names: table, tabular, big table, column family, columnar store, generally somewhere in the space. I'm going to explain what is a column family soon, but essentially tabular stores, table stores, these sorts of names. Yeah. So the idea is we're going to be storing columns. We're going to be storing tables. So a key value store is a distributed map, and essentially a tabular store is a generalization of that, where we're going to have multi-dimensional values in our maps. So we're going to structure our values just a little bit. in order to have multiple dimensions that we can reference. So now we see that we can explicitly represent not just a simple value, but we can have tuples that have attributes or columns that we can reference. So one of the more influential papers, again, along these lines was the big table paper, published by Google this time. They, again, as in many of the cases of the things we saw, the company published a white paper, explained how they were using this technology, and then other people took this white paper and implemented the ideas in open source alternatives. So Big Table was used within Google to manage semi-structured data for all these cool applications. I'm sure everybody remembers ORCUT. So we have Google Analytics, we have Google Earth, we have metadata relating to searches and so forth. So essentially Google has needs for managing semi-structured data as well. So Big Table in a nutshell, we're given 3 elements. We're given a row, a column, and a time, and we map this to a value. So a time is essentially a versioning information. So for example, given this table here, we can map Afghanistan population value, which is the attribute name or the column, T4, which is the timestamp, and then this gives us a particular value, which is the population of Afghanistan in this timestamp by intersecting T4 population value in Afghanistan. So we get some value for the population back. One thing that's interesting about Big Table compared to Dynamo is that we have sorted keys. So this is another very common style of storage for NoSQL systems, where rather than just hashing individual keys, what we're going to do is store them and define an order over the keys. So in this case, we see we have some sorted order over the keys that we have. So this gives us certain benefits. So one of the benefits is that we can do prefix searches on our keys. So we could find, for example, all the keys starting with Asia more easily because they're all going to be in order. So it should be easier. Another benefit that may not be at all obvious is we'll see in a second. Yeah. So we have range queries, so we can do prefix lookups. We can find all the keys that start with a letter between A and C and so forth. And we also have locality of processing. So the idea is that by having ordered keys, we can do some processing locally within certain regions of our table. Yeah. So we'll have here naturally, for example, if we define our keys in a certain way, we'll have a region of our table related to Asia, and we'll have another region of our table related to Europe, for example. So we have some locality of processing that this enables for us. So a much better example of locality, because if we just look at countries, there's like 200 of them, and it's hard to imagine this at scale. But a real example of locality is for their web index, for their search metadata. So what we have here is essentially the web page as they should have been defined originally with the top level domain first, but unfortunately that's not the way the web was defined. It was defined the other way around. So this is a very common normalization for people who work with web data. They put the domains in the reverse order. Why do they do that? Because if you order the thing, if you sort it later, you actually get it in the expected order. Yeah. In the same way, people rather prefer year, month, day, rather than the other way around. So if you order, it gives you the domain and then the subdomains and then the paths and so forth. So ordering the data in this way, rearranging the domain and ordering the web data in this way, we get locality of processing, which means that we have certain sections of our tables will refer to certain websites. And we can, just by processing that sort of locality or region of the table, we can process or aggregate data for a particular website, for example. So this is quite nice. So in terms of distribution, this changes how we do distribution quite a bit. So the idea now is that we're going to split by tablet, which would be blocks of ordered data. We're not going to split by hash. So if we want to look up a given key, we would need to know in what tablet it's in, and then we need to know what machine has that tablet associated with it. So this is called horizontal range partitioning. It's an important concept that's used. Some NoSQL systems use it, others do not. But it's important to understand what horizontal range partitioning is in order to understand if it's suitable for your application, if you're going to have range queries or locality of processing and so forth. So I mentioned before that sometimes these systems are called column families. What is a column family? So Big Table defines this notion of a column family as essentially a group of related columns. So we can group together certain columns that we're going to access together, or that we want to define different storage or access control for. We can group certain columns into a column family. So in this case, we have a political column family related to political data about the country. And in this case, we have some demographic information, which groups together the population value and the population year. So essentially, these column families we can read independently of each other without having to read the other column families in the same table. Yeah, so they're sort of data that are stored together and can be read together very efficiently. And we can also define access control at the level of column families. And this is where the name column family store sometimes comes from. So if you want to read more, again, there's you can check out the white paper by Google, Big Table, a distributed storage system for structured data. Again, you don't use Big Table. Big Table was not available. The new version of Big Table is now BigQuery, which Google offers, which is a somewhat different design. However, Big Table was implemented as some open source alternatives, including HBase, Apache HBase, and what became more popular than HBase eventually, Cassandra. Yeah, so Cassandra evolved from a sort of key value store, and then it's essentially a tabular store now. So Cassandra is the system we'll use in the lab. So I'm just going to spend the very last part of the class just to talk a little bit about Cassandra. Few slides, and then we're done. Oh, I took these slides from a Spanish class, but anyways, tabular store. So we have here a table. We have sales with product, store, client, date, and value. So we have some data organized into columns in Cassandra, and we can store this in Cassandra, but we can then query that table using the Cassandra query language, which is essentially a very, 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 very minimalistic version of SQL. Yeah, so with maybe a few other different features that SQL does not offer. So essentially, we have SQL where we can't do group bys, we can't do joins, we can't do very much except for just select from where, and where is a simple condition. Yeah, so we can only specify one table, and then our where is just a simple selection condition over the tables. No joins, no group by. Well, there's a group by here, but this is this is a very limited form of group by that we can use. So the idea is that Cassandra only allows you to write very efficient queries that it can run efficiently. So what this means basically is that it will block you from doing anything that it feels will be too expensive. You know, it just won't let you write the query. In some cases, you can add, for example, allow filtering to say that in certain cases, I know this query might not be the most efficient, but I don't care. I want to run it anyways. So the non-SQL things that we see here are JSON, which allows us to return results in JSON format rather than a CSV or a table or what have you. We can represent our data in JSON. We have a per partition limit, which will limit the number of rows that we will receive per partition. So it allows us to receive a certain number of elements from different partitions of the data, which we'll talk about in a second. And allow filtering, which basically says that, okay, I have a query, I have a selection condition, I don't have an index for this, but I'm okay with running the query and reading lots of rows and then filtering them afterwards based on the selection condition. So basically it means that there isn't a super efficient way to read only the results for this query. Rather, we're going to have to read more rows and filter them afterwards according to the condition. And this says that I'm okay with that, and I understand that, and Cassandra will warn me that this is going to be slower than usual, and it's not Cassandra's fault. And okay. So as an example of a query in Cassandra, we have this SQL statement here. Select star from sales where product equals comfort and value is less than 2,500. And we see here the rows that have been extracted. So this is a typical CQL query. It's basically like a very simple version of SQL. I think I know what I did now. I think I translated. So I took this from a Spanish version, and I probably translated the slides in the Spanish deck to English because I definitely translated this stuff. So, and I left this in Spanish, but whatever, you guys understand. So there's primary key. So where we have, no, because I translated sales here. I don't know what I did. I'm very confused. Anyways, so sorry for the Spanish. So we have primary key and we have a sales table. So this is probably the most important concept to understand for Cassandra, and it's something that's not intuitive at all. If you come from relational databases, it's actually kind of a little bit weird. And the other thing I must do, I'm sorry, is that this is incorrect, but I can change that quickly. Yeah. Okay. So we're going to define a key, primary key, as in a relational database, for example. So our primary key is going to consist of two parts. The first part is the partition part, and the second part is the order clustering key. So in English, we would call this the clustering key. So we're going to use the partition key, product and store, in order to decide on what machine to store the data. So we have producto and tienda, product and store here. And we see that we have all of the rows with the same product and store will be stored on the same machine. Yeah, so we use these two columns in bold to decide on what machine to store the data. Within each partition, we can then choose an order. We can sort the data in a particular way. So we can sort the data here, for example, by date and by client. So we're going to order by date first and then by client. Yeah. So then based on this, Cassandra allows you to answer certain types of queries or questions. So the types of queries or questions we can answer in Cassandra based on this key, we have to specify the partition key, the full thing, because Cassandra needs to know on what machine the row is. So it will accept, based on this definition of a primary key, it will accept queries where we specify the product and the store. For example, Nescafé Providencia. We can do select star from sales where product equals Nescafé and store equals Providencia. And this is a perfectly valid query, okay? Within each partition, we can then also order by fecha and cliente. So we could say, for example, Nescafé Providencia, and then define the date before March 31st, 2020, for example. We can do range on that. So it has to go in the order in which the elements are presented. So in the lab on Wednesday, you're going to be you're going to play with this, or you're going to have to design a primary key in order to be able to answer certain types of queries. And in general, the key here is that we always need to give the partition key. And once we give the partition key, we can't leave any gaps. So we can optionally add date, or we can optionally add date and client. We can also add a range on the last element. So we can have product store and then less than date or greater than date, or we can specify product store date and then less than client, greater than client. What we cannot have, for example, is specify just product, yeah, because we need to give the full partition key. And we cannot say, for example, product store client. We can't skip date because the data are in order of date and then client. So we would have no way to do the search properly. So that's they're the details for Cassandra. That's the introduction to NoSQL. So these systems are becoming more and more popular for applications, particularly where we don't really need NoSQL. We need we don't need SQL. We need perhaps a simpler abstraction would be sufficient, and we can do that more scalably and more efficiently. So we'll have 2 more classes on NoSQL, and that would be essentially the core content of the course. We'll also have a conclusion class where we'll go through some scenarios and what kinds of tools we can use for that. Any questions or doubts? All good? Any questions on Zoom? So what is the real color of the dress? The real color of the dress is blue and black. There's a good diagram on Wikipedia that explains it, but it really was blue and black. It doesn't have a color as blue and black. And all the people who see it as white and gold are just very strange. Okay. So on Wednesday, we're going to see Cassandra. And yeah, that's it. So if there's no questions in Zoom, have a good rest of your day. See you.